Okay. Good afternoon, students. Welcome to the Real Analysis live lectures. So, in previous lecture, we have seen what is open set and some of the theorems on open sets. In that, we have seen every open interval is an open set. Then, every subset of discrete metric space is open, right? And also we have seen every open ball is an open set. Now in today's session we have to see remaining theorems about open sets. Okay. So next theorem. I will state the theorem. Any open set U in M can be written as union of open balls contained in U. So what is the statement? We want to prove any open set U in metric space MD can be written as union of open balls, which will be totally contained in U. That is U is equal to, we have to write union of B epsilon of X such that B epsilon of X is totally contained in U. Okay, this is union, okay? This is union and this is U. Okay, so this is easy. How we can prove this? Again, we have to show two sets are equal. So we will show one is contained in another, other is contained in first one. Then both will be equal sets. Okay. So which one is trivial? Which one is trivial? B epsilon of X is contained in U. So union will be again contained their union will be obviously contained in U. Are you getting? I want to prove.
Yes.
This U is contained in union of B epsilon of X, so that B epsilon of X is contained in U, and another one is union of B epsilon of X, so that B epsilon of X is contained in U. This I want to show that it is contained in U. So how I can show this? Which one is trivial? First one or second one? If I show this 1 and 2, then I will say that both are equal. So which is trivial? Which one is trivial? Since B epsilon of X is contained in U. Whether it will imply their union also contained in U?
Yes.
Yes or not?
Yes, ma'am.
Yes. So to prove other way. To prove another way, what I have to do? I want to prove now U is contained in union of open balls. So how I can prove this? Let X belongs to U and show that this X belongs to union of open balls. Okay. This X belongs to union of this open balls. So X belongs to U. If X belongs to U and as U is open, what can I say? since U is open, what will happen? There exists epsilon greater than 0 such that what? X belongs to B epsilon of X, which will be contained in U by a definition of open set.
Yes, ma'am.
Yes. So what this implies? X belongs to B epsilon of X, which is contained in U, means what? X belongs to union also?
Yes, ma'am.
B epsilon of X, which is contained in U. So this gives me what? This implies U is contained in union of B epsilon of X such that B epsilon of X is totally contained in U. So from 1 and 2, the theorem is proved. U is nothing but, U can be written as union of open balls, which is totally contained in B epsilon of X is totally contained in U. Is that okay?
Yes, ma'am.
Now we want to prove next theorem. An arbitrary union of open sets is open. We want to prove arbitrary union of open sets is open. That is, if U alpha belongs to lambda is an directed set, is any collection of open sets, then what I want to show, their union over alpha U alpha, union alpha U alpha is open, is also open. We want to prove. Okay. So how to prove this? What is given? Arbitrary union. We want to prove arbitrary union of open sets is open. So each U alpha is open and we want to prove their union is also open. We don't know what is that union, whether finite union, arbitrary union means any set you can take. Okay, alpha belongs to directed set. It may be finite, countable, uncountable set, whatever. That directed set can be any set, but still that union U alpha will be open set. Okay, so how can we prove this? We'll denote this set by some another name. Let V is equal to union alpha belongs to lambda U alpha. And what is my claim? I want to show this V is open set. Okay, I want to show this V is open. When I will say some set is open, if for every X in that set I can have some open ball which is totally contained in that set, then I will say it is an open set, right?
Yes, ma'am.
So we will, whenever we want to show some set is open, what we will do? We will start with arbitrary element from that set and we will show there exists some open ball which is totally contained in that set. So, we have denoted V is equal to this set and let X belongs to V. Take arbitrary element from that set. So what can I say? This X belongs to U alpha. for some alpha, right? कोणत्या तरी एका सेट मध्ये असेलच ना तो x belongs to union means x belongs to u alpha for some alpha, right? Yes. And now u alpha, how is u alpha? U alpha is open, right? Since u alpha is open, what can I say? There exists epsilon greater than 0 such that x belongs to b epsilon of x, which is contained in what? U alpha, right? Now but this u alpha is contained in union also. Union alpha belongs to lambda u alpha, and which is nothing but my v. So this implies x belongs to b epsilon of x, which is contained in v. Therefore v is also open. V is an open set. Is that right? So arbitrary union or arbitrary collection of open sets is also open. Is that okay?
Yes, sir. Yes, ma'am.
Now we have to prove another theorem. Finite intersection of open sets is also open. That is, if u1, u2, un are open sets, then intersection I is equal to, I is equal to 1 to n ui is also open. We want to prove this. So how we can prove? Again on same lines. So let denote this, whatever set we want to show open, denote by v. V is equal to intersection I is equal to 1 to n ui. I want to show this v is open. Okay. So how I will start? Again, start with arbitrary element from v. So take and x belongs to v. So for this x, I want to find some open ball for which this x is center and which is totally contained in v. Then I can say that this v is an open set. Am I right?
Yes, sir.
Yeah. Now this x belongs to v means what? X belongs to intersection of ui. Intersection I is equal to 1 to n ui implies x belongs to ui for every I. For every I,
Yes,
x belongs to ui for every I. And now since each ui is open, since each ui is open, what will happen?
There exists open ball.
Yeah, there exists epsilon I greater than 0 such that x belongs to b epsilon I of x, which is totally contained in ui, right? So
Yes, ma'am.
yeah, for every ui there will be one epsilon I, for which that x will be contained in b epsilon I of that open ball and which is totally contained in that ui. Now can you give me one open ball which will be contained in intersection of ui's? Are you getting this? I am having different radius. I am having x. Suppose this is my x. This is x, and this is, say, one open ball. This is another open ball. This is another open ball of different radius. Say this is epsilon 1, this is epsilon 2, say this is epsilon 3, and so on. For every I am having one epsilon I. For every ui, I am having one epsilon I such that x belongs to b epsilon I of x, and which is totally contained in ui. So can you give me one epsilon from these epsilon i's, can you give me one epsilon or radius for which that ball will be totally contained in that intersection? Whichever is minimum, that will work.
Yes, ma'am.
Yeah, because this will work from here. Epsilon 1 will work, but we don't know what is epsilon 1, what is epsilon 2, what is epsilon 3, and like that. I am just giving here arbitrary numbers. Okay, so let take epsilon is equal to minimum of epsilon i's. Okay, I is equal to 1 to up to n, minimum of this one. Then what can I say? Then this x belongs to b epsilon of x also, and which is contained in ui for each I, for all I, right? Are you getting this?
Yes, ma'am.
Yeah. So this implies x belongs to b epsilon of x, and which is contained in intersection I is equal to 1 to n ui. That is nothing but my v. So this implies v is an open set. Is that okay? So finite intersection of open sets is open. But what can I say about arbitrary intersection? Arbitrary, but note that remark, arbitrary intersection of open sets need not be open. Intersection of open sets need not be open. Need not be open. So if I want to show this, then I have to give one counter example, at least one counter example for which it is not true. Like arbitrary intersection of open sets, if I take, it is not open, right? So for example, consider the sets. Consider the sets un is equal to minus 1 by n, 1 by n. These are open intervals.
Yes, ma'am.
Which are
Yes,
open intervals in R. They are open sets. That is, each un is open set. Each un is an open set. But what is their intersection? I is equal to, or n is equal to 1 to infinity. What is this intersection? Intersection n is equal to 1 to infinity minus 1 by n, 1 by n. What is this intersection? Can anybody tell me what is this intersection? We'll draw the figure. This is real line. For n is equal to 1, what is this set?
-1,
Suppose if I this instead of this, -1, right? So this is -1, 1. Now for n is equal to 2, what will be this? This is my u1. -1 to 1 is u. I will write here. What is u1? u1 is nothing but -1, 1. What is u2? Minus half, half. What is u3? Minus 1 by 3, 1 by 3, and so on. So half will be somewhere here. I will denote with different color. This is say u2. Okay. Where will be u3? u3 will be somewhere here. u4 and so on. Okay. So as n tends to infinity, where it will go?
0.
It will go to 0. So what is intersection?
0.
It is singleton 0. And we know that singleton 0 is not open in R. Which is not open in R. Open set in R. Right? Singleton sets are not open in R with respect to usual metric. Okay? Am I right?
Yes, ma'am.
Because you cannot have an open ball which is totally containing open that singleton set. Okay. Now next theorem. Yes.
If you take finite union of open sets,
It will be open. Because arbitrary union of open sets is open, we have already proved. Finite, countable, uncountable set, whatever you take. If union is means whatever union of open sets you take, it will be open.
yes, ma'am.
Okay. Now we'll take the theorem. Already we have proved that theorem. If this we will write as a remark, not necessary. Remarks. If U is an open set in R, then U may be written as countable union of disjoint open intervals. If U is any open set in R, then U can be written as countable union of disjoint open intervals. That is, U is equal to union I is equal to 1 to infinity In, where In is nothing but open interval an, bn, and how are that intervals? They are disjoint. In intersection Im is empty for all n not equal to m. Okay. So if U is an open set in R, then U can be written as disjoint union of open intervals. Countable union of disjoint open intervals. Okay. So after this we will take a theorem. Now we will take a theorem. A set U in metric space MD is open if and only if whenever a sequence xn in M converges to x in M, x in U, not M, x in U, then xn belongs to U for all but finitely many. For all but finitely many. This is if and only if statement. What we want to prove? A set U in metric space is open if and only if whenever there is a sequence xn in M which converges to x in U, then xn belongs to U for all but finitely many. Okay, so we will prove. First we will assume, suppose U is open. Suppose U is open in MD, metric space MD. And what I want to prove? I want to prove there is a, whenever xn converges to x in U, then xn belongs to U for all but finitely many. So let xn belongs to xn कुठे है? Where is xn? Xn from where I have to take xn? Xn in M. So let xn belongs to M such that xn converges to x belongs to U. And what I want to show? I want to prove xn belongs to U for all but finitely many. Okay. Now, since x belongs to U, what is my U? U is an open set and U is an open. What will happen? There exists epsilon greater than 0 such that B epsilon of x will be contained in U, right? By definition of open set. Am I right?
Yes.
Yeah. And what is given? And also how this xn is given? Xn converges to x. Also as xn converges to x, for this epsilon greater than 0, what will happen? For this epsilon greater than 0, what will happen? By definition of convergence, there exists natural number n belongs to capital N such that what? Not modulus. Now it is a metric space, general metric space. So distance of xn x is less than epsilon for all n greater than equal to n, for this natural number n, right? So what this implies? What this implies? Xn belongs to where? From this step, what can I write? Xn belongs to which ball? B epsilon of x for all n greater than equal to n, right?
Yes, ma'am.
Yes. So this implies xn belongs to b epsilon of x, but this b epsilon of x is contained in u for all n greater than equal to n. Means this implies xn is contained in u for all but finitely many. Finitely many. Right? Now to prove converse, now to prove other way, to prove converse, what we have to assume? Suppose now, suppose whenever xn converges to x in u, xn belongs to u for all but finitely many, and we have to prove then u is an open set. So to prove converse, on the other hand, on the contrary, assume, we will prove this other part by contradiction. Okay, on the contrary, assume u is not open. U is not open. Okay, so if u is not open means what? By definition, if u is open, by definition, what is?
Then
Yes.
then open is not totally contained in U.
Not containing.
So not totally contained in U.
If u is not open.
Yes, because it is open, then ball is totally contained in that set. No?
Huh. And if it is not open, then it is not contained.
Yes.
It is not contained. Wait, 1 second. By definition, what is mean by u is open? There exist for every I will write here by definition. U is open means for every x in u there exists epsilon greater than 0 such that b epsilon of x is contained in u, right? Now I want negation of this. U is not open. Not open. So u is not open means what?
X doesn't belongs to U.
There exists x belongs to u such that
Their open ball does not contain in U.
at least one b epsilon of x does not contain in u for every epsilon greater than 0, right? For every epsilon greater than 0, b epsilon of x does not contain in u. Means u contains at least one element for which we cannot have a ball, open ball with center x, which is contained in u, right? Are you getting negation? When you are doing negation of a statement, for every will change to there exist, and there exist will change to for every, right?
Yes, ma'am.
Yeah, you can see here this for every, then there exists this, there exists epsilon here for every epsilon, and this condition will become negation of that condition. Is that right?
Yes.
Okay. So now if u is not open, then let me take below. Yes. Since u is not open, there exists I was using this. There exists x in u such that b epsilon of x does not contain in u for every epsilon greater than 0. So in particular, for epsilon is equal to 1 by n, also for epsilon is equal to 1 by n, there exists xn belongs to b1 by n of x, but xn does not belongs to u, right? So this implies distance between xn and x is strictly less than 1 by n from here. What is distance between xn and x? Which is strictly less than n, and as n tends to infinity, what it will tends to? Distance between xn and x, it will tends to 0, right? So this implies xn converges to what? Xn converges to x in this D, right? In this metric D. Therefore, by assumption, x, where is x? X belongs to U, and we are saying xn is elements in this ball which is contained in M. Xn converges to x in U we are having. So by assumption, what I should have? Xn belongs to U for all but finitely many. Right? And which is contradiction, because what we have started with, xn does not belong to U, right, for all n, which is contradiction, as xn does not belongs to U for all n, and hence U must be open. So our assumption was wrong, and therefore U must be open. Is that okay? Is that okay?
Yes, ma'am.
So now we will define, next one is closed set. Yes, closed set, a set F in metric space MD, is said to be closed, if its complement is open. If its complement is open, that is, if F complement is open. Again, that is for every x in, what is mean by F complement is open? That is, for every x in F complement, there exists epsilon greater than 0 such that B epsilon of x is contained in where? F complement. So F is said to be closed if its complement is open. Okay. For example, what about trivial closed sets now? M and phi are closed sets because what is their complement? M complement. What is M complement? Whole space complement is empty. And what is empty set complement? It is whole space. They are open already. Which are open sets. Right? Which are open sets. Therefore, whole space and empty sets, they are open as well as closed sets. These are trivial sets. Okay. Second, every closed interval is a closed set. Is a closed set in R. Interval means it is from R only. Why every closed interval is closed set? You take AB, closed set, closed interval will be like this, AB. So its complement. What is its complement? What is its complement?
Open interval AB.
The complement means what? Like this, no? If this is your A closed, no? Closed sets, closed interval A, B, wherever it may be on real line. What is its complement? Complement will be union of these sets, right? Union of these sets. This is complement. Union of these two sets, right? Complement means R minus this set. Okay, so what is that set? Minus infinity A, open A, union B, infinity, right? And these are open intervals already. So open interval are open sets and union of open sets is open, right?
Yes, ma'am.
Yeah, so these are already open sets. This is open set. This is also open set, and union of open sets is open. So complement of this closed interval AB is open. Therefore, which is open set. Therefore, closed interval AB is closed set, right? Okay. Now, again the same lines as we did for open sets, there are three theorems. What we have proved? Arbitrary union of open sets is open, we have proved. Now here for closed sets theorem, arbitrary intersection will be closed. Arbitrary intersection of closed sets is closed. We want to prove arbitrary intersection of closed sets is closed. So how we will prove this? Start with arbitrary intersection. So let F alpha belongs to lambda, arbitrary directed set, be closed sets. So if each F alpha is closed, so what can I say about its complement? This implies, what about its complement?
Is open.
Is open set for each alpha belongs to lambda. But we know that arbitrary union of open sets is open. So union alpha over directed set F alpha complement is also open, right?
Yes, ma'am.
Yeah. But by De Morgan's law, what is this union F alpha complement? Intersection F alpha alpha belongs to directed set and its complement is open by De Morgan's law, right? Since union F alpha complement is nothing but, or I will write instead of this De Morgan's law. De Morgan's law everybody know? By
Yes, ma'am.
De
Yes, ma'am.
Morgan's law. So now if this complement is open means what can I say about that arbitrary intersection? What can I say about that arbitrary intersection?
Closed.
It is closed set. It is closed set. Is that okay? Now we already proved. Now next theorem. Finite union of closed sets is closed. Is closed. So again, for this what I have to do? So let F1, F2, Fn be closed sets, and I want to show their union is closed. Okay, I have taken finite F1, F2, Fn be closed sets. So if F1, F2, Fn are closed sets, what can I say about their complements? F1 complement, F2 complement, Fn complement. These are open sets.
Open.
Yeah. Now what I know about finite intersection? Finite intersection of open sets is open.
Yes.
Intersection I is equal to 1 to n Fi complement is open because finite, we already proved finite intersection of open sets is open. Open sets is open. Therefore, this intersection is open. Now, what this implies? Union I is equal to 1 to n Fi and its complement is open by De Morgan's law. I have used De Morgan's law, right? So this implies union I is equal to 1 to n Fi is closed set. Is that right?
Yes, ma'am.
Okay.
Yes, ma'am.
Now, what will be the remark then? Can anybody guess? Finite union is closed. So what can I say about arbitrary union? Need not be closed. A remark. Arbitrary union of closed sets need not be closed. So for this again I have to give one example. For example, let Fn is equal to I will take 1 plus 1 by n So union of this fn's is nothing but open 1, 3 and which is not closed set. Okay. Therefore, arbitrary union of closed sets need not be closed. Is that okay?